biggest project that we probably took on was developing what we call the Ultima 2Pplus, which was a re-envisioning of the original system from 2004 that kept a lot of the same architectural elements of the system with multi-path scanners, but we decided to make everything bigger. And so we listened to our customers, and we were pushed to see if we can, first of all, expand the field of view, which we did, in both not only the traditional high-resolution Galvo mode, or the slow scanning mode, but also the resonant mode, which is the mode that allows for video rate imaging with 2-photon. And so we were pushed to also improve our SNR, our signal-to-noise ratio, and we did that by increasing the size of all our optics, not only on the excitation side, but on our emission side. So we moved to all 50-millimeter collection optics to capture all the challenging photons that you generate deep within tissue. We moved our compatibility of wavelengths, or broadband capability, up to 1700 nanometer as well with our optics to allow for not only 2-photon imaging, but 3-photon imaging to go even deeper. We tried to do this without compromising any performance, and so you get the same performance and imaging quality at the center of your field of view as you do at the edge of the field of view. And what I'll talk about more is we also enabled a 3D holographic photo stimulation experiment, not only on the stimulation side with our SLM, but also the 3D volumetric imaging side of things as well. So you can actually look at your neurons in 3D while doing your photo stimulation. And so what I show here on the right is actually one of the first data sets that we collected on the Ultima 2Pplus, which is its calcium imaging in mouse cortex. This is thanks to Adam Packer's lab at University of Oxford that shows that now you can correlate neurons that are far away because of our larger field of view. So we can make these connections of neural activity at the center of your sample as well as near the edge of your sample. And so one thing that the large field of view also gives you, in addition to being able to correlate live neural activity, is if you wanted to image tissue, large piece of tissue at that, and you wanted to tile your scanning across this large tissue, now this kind of tissue tile scanning actually takes a lot less time because each field of view is made up of much larger tiles. And you still retain the high resolution capability and being able to look at fine structure if you look at just each individual tile, which is a property of spending the time and effort to maximize the imaging quality. On this slide, this shows some of our re-engineered excitation paths and emission paths. So on the left is our custom relays now we're able to create with Bruker's R&D investment, that we're able to make all custom optics now that maximize the field of view and imaging quality, as well as the broadband capability of it. So this is our resonant relay lens that's actually a large optic that is almost the size of a soda can that we're able to create now. And in the middle is our large filter cubes that we moved to. And so the smaller filter cube to the right of that large filter cube is kind of the standard 2-photon emission cube. That's 25 millimeters. But we've moved to 50 millimeter kilo cubes in order to maximize the collection. And this is important because as you image deep, as shown by the image on the right, photons come back more scattered, right? There's a better chance of scattering as you're imaging deep, and the photons come back at this higher angle, which because of that, you need the higher aperture or bigger aperture in order to capture these challenging photons.